You type a few words, hit enter, and seconds later, you get a masterpiece. To do this, computers use a diffusion model. Think of it like a digital sculptor, but instead of starting with a block of clay, it starts with pure chaotic static, what we call digital noise, and slowly carves out an organized picture. It feels like the computer already knows what it wants to draw, but it actually has no master blueprint. It is completely blind, just chiseling away at the noise, pixel by pixel, hoping to find a recognizable shape. Because it can't see the big picture, the machine has to make millions of cautious calculations. It checks its work over and over to ensure it doesn't accidentally ruin the image it is trying to build. This diagram represents how the computer navigates that digital noise. To figure out which direction to carve, the software relies on a mathematical tool called a score function. You can think of this as a very simple compass. It can't show you the final destination, but it points the computer toward a slightly cleaner, less noisy cluster of pixels nearby. Because the computer is feeling its way in the dark, it has to take agonizingly small steps. It moves a fraction of an inch, stops, checks the compass, and moves another fraction of an inch. If the machine gets impatient and tries to take a giant leap forward based on that simple compass reading, it easily veers off course. It misses the target completely and ends up lost in a mess of random pixels, ruining the image. Taking these tiny steps is safe, but it requires massive amounts of processing power and time. This cautious baby step approach is the main speed limit holding back the software we use today. We measure how perfect an AI's best is using a concept called target accuracy. If you just want a rough sketch, a passing grade, the computer can finish fairly quickly. But if you want a flawless, high-resolution masterpiece, the grading gets much stricter. Pushing these older models to reach that level of perfection causes their computing time to multiply. To get an image that is 10 times sharper, it might take 100 or even 1,000 times longer to process. A team of researchers from MIT looked at this bottleneck. They realized you don't necessarily need a perfect map to take large steps safely. You just need a better way to test the ground before you jump. Working with colleagues at Yale University, they developed a mathematical algorithm that allows the computer to leap forward without paying that massive time penalty. Instead of pouring billions of dollars into building larger supercomputers to process those tiny steps faster, they rewrote the underlying rules of how the software navigates information. Their solution is an algorithm called First-Order Rejection Sampling, or FORCE. If the old method was a simple compass, FORCE is like giving the computer an advanced radar system. This graphic shows how the algorithm calculates its path. Instead of taking a tiny step, it projects a massive leap straight across the noise. Before actually moving, it flips a weighted mathematical coin, a probability test, to predict whether that exact landing spot is safe. If the test predicts that the proposed leap will land in a chaotic area and ruin the data, the algorithm rejects it. It instantly deletes that path and calculates a new one. But if the test determines the landing spot is safe, the computer accepts the leap. It snaps its position forward, entirely skipping the thousands of cautious baby steps it used to take. By confidently testing and skipping over large areas of noise, FORCE cuts generation time drastically. It operates like an expert sculptor, knocking away huge chunks of marble in a single strike, rather than scraping it away slowly. This radar system works because our data has a secret weapon, a hidden simplicity. An image might be made up of millions of random pixels, but the rules that make a face look like a face are quite simple. By focusing on those core rules, the computer can ignore the noise and move much faster. Taking advantage of this simplicity allows the algorithm to reach perfection without the usual time penalty. It answers the question of how to be incredibly fast and incredibly accurate at the same time. When you place the old method next to the new algorithm, the speedup is obvious. One side is still chipping away at the static, while the other clears the board in large, sweeping motions. The math behind these faster images applies to high-stakes scientific research too. Meteorologists use these same diffusion models to process massive amounts of atmospheric data, simulating global weather patterns and predicting climate shifts. In hospitals, similar software reconstructs high-resolution medical scans from noisy sensor data. In these situations, achieving high accuracy isn't an aesthetic choice. It is required to give a patient a correct diagnosis. The time it takes a computer to generate an accurate model in these fields is the primary bottleneck holding back major scientific discoveries. For biologists, this algorithm can accelerate drug discovery. Instead of spending years waiting for computers to calculate how complex molecular structures fold together, they can generate accurate models in a matter of days. These researchers have shown that we no longer have to choose between processing speed and high accuracy when building artificial intelligence. We can have both. Teaching a machine how to smartly reject a bad leap, rather than forcing it to walk in cautious baby steps, frees up massive amounts of computing power. By removing the old mathematical speed limit, researchers have turned a major bottleneck into a fast lane for discovery.